Welcome to Solarius PV, the ultimate ACCA software solution tailored for PV system designers and installers. With its intuitive interface and a one-of-a-kind step-by-step assisted design editor, Solarius PV is your software tool for sizing and assessing grid-connected photovoltaic systems. Now, let's explore how Solarius PV can revolutionize each stage of your design process. From conducting thorough site assessments to in-depth solar radiation studies, this software ensures accuracy at every step. But that's not all. Solarius PV goes beyond by simplifying the creation of construction documents, design layouts, single-line electrical diagrams, and detailed financial analyses. Picture this: you effortlessly navigate through the design phases, armed with a powerful tool that not only enhances precision but also transforms complex data into clear, concise visuals. The result? You present your clients with a feasibility analysis that's not just accurate but impressive too. Get ready to embrace efficiency and precision like never before with Solarius PV. Upon launching the program, the homepage appears. This section offers a straightforward way to create a new project. You can choose between a new low-voltage system, a low-voltage three-phase system, or a medium-voltage system. Let's start by creating a new project and embark on the easy step-by-step design process. Upon creating the new file, the program opens a tree node structure on the left, guiding you through the logical steps of defining your project. In the General Data section, you'll find Client and Designer nodes. Here, you can input all relevant client data and your design firm's information. One of the key design aspects of Solarius PV is characterizing the solar radiation data required for system sizing and design. This data helps determine if a site is suitable for a PV system. Let's use the specific Open Location Archive tool to search for a location, such as Balbriggan in Ireland. As you can see, the geographical and irradiation data are automatically loaded. This dialog allows access to an archive of locations worldwide, organized by cities and provided by the Mateo norm. It includes horizontal plane solar radiation values for each city. But what if my location isn't present in the archive? Well, in this case, you can switch to the User tab and add it using the three main data entry methods. Of course, it is possible to manually enter location name, coordinates, and add monthly irradiation data. While entering the average daily radiation, the chart will be updated dynamically. You can also import data from the PVGIS portal for various European, African, and Asian locations. Or you can use the Google Maps locator. This allows you to import location data using the Google Maps locator to retrieve solar radiation data from Medianorm 7.1, along with the site's altitude values. The software provides an irradiation chart that displays a monthly average energy map organized based on hourly distribution. You can easily switch between different data viewing modes. Solarius PV streamlines the process of obtaining solar energy data for various locations through two distinct solar databases. The data is readily accessible at the click of a button. With these tools, Solarius PV simplifies the process of gathering essential solar radiation data for your project, making it an invaluable asset for architects, engineers, and BIM specialists in the construction industry. Let's explore more of its features and capabilities to enhance your PV system design experience. Let's step ahead in the shading factor section. Here you can determine the shading factor in two ways. Providing that you know a known shading factor value, in this window you can manually enter the exact value. The second method involves a calibration process, aligning a 360-degree panorama photo with the solar diagram of the selected location. The automatic calculation is activated after defining the location's photographic survey in the program. In this particular phase, we'll now see how to set the sun's correct position and location's cardinal data acquired on-site. We will use one of the many clinometer apps available for our mobile phones, such as, for the sake of this example, SunQuest. It's a mobile app available both for Android and iOS. During the survey, it's important to acquire the elevation angle against the horizon and also take note of the correct orientation of some reference objects using the clinometer app. These main references will then serve the purpose of aligning solar diagram correctly. So, let's start off by setting up the solar diagram by adding our 360 panorama photo taken on-site. Once the image is set as the background, the next step is to get the information previously acquired from the clinometer app to calibrate the south and north directions using the vertical axes and the elevation angle. You can see that all we need to do is get the elevation reading, in this case 9 degrees, and input that value in the field. The site inspection sheet provided with the software can come in handy to note down the info while at the installation site. Now, if we've done a good job of the solar diagram calibration process, you should even see the sun path simulation align correctly for the specific date when the photo was taken. We already saw how to import a single 360 panorama in the solar diagram, but the software can also process multiple shots, stitching the images and creating a single landscape background. Now that we have this new panorama, let's see how to fine-tune some properties of the diagram in order to obtain a more accurate output. The software calculates the system's efficiency based on azimuth and tilt values for that specific location. It highlights the importance of an optimized module positioning, considering factors such as hills, mountains, trees, and buildings that may influence solar radiation. You can define the shading factors and seasonal shading percentages. Here we will apply some modifications, keeping an eye on the shading factor to see how its value will change. Of course, the first step is always the south and the vertical calibration, as well as the date and time of the phot shoot session. This time our elevation reference point will be the top of the tree, which, from the surveyor's point of view, has an elevation of 28 degrees over the horizon. Therefore, let's move this reference line to the new position, setting the vertical calibration of the solar diagram. At this point, the shading factor value is still 1. In order to change its value, we need to insert all those landscaping objects that can create an obstacle to the sunlight, starting from the land profile at the horizon. And as consequence, now notice that the shading factor now is 0.97. We can improve our accuracy by inserting the vegetation. Clearly we can concentrate on those elements that can effectively create an obstacle, and now our shading factor is 0.94. For improved accuracy, we can define how the effects due to vegetation during the various seasons can affect the shading factor and insert a value for each month of the year simulating the effects of shadowing. Consequently, the shading factor is a bit higher now, with a value of 0.95. Lastly, we can insert other objects such as the building, which in this case are not particularly influencing the shading factor at all. All of this valuable information empowers us to implement the system for maximum irradiation while considering effective positioning, accounting for architectural and landscaping factors. The albedo coefficient, found in the Reflectance tab, helps us assess the energy surplus due to surface reflectivity. In general, dark surfaces have a lower albedo value, while lighter ones have a higher value. Now, let's proceed to the system design process by clicking the BIM System Design button. Within this modeling environment, you'll discover dedicated BIM objects tailored for PV system design, encompassing surface types, generator types, switch panels, and inclined surfaces. Additionally, generic modeling objects like 3D models and the generic building volume are available. In the Drawing Model section, leverage the IFC Object Import tool and drawing composition tools to create plan views, cross-sections, elevation views, and 2D graphical objects, enhancing your drawings. Let's zoom in on inserting the inclined surface object in the site plan. You can import a CAD drawing in DWG or DXF format, serving as a background for tracing surfaces. Enter the dedicated editor, select the horizontal surface, and outline a simple perimeter. Switching from horizontal to sloped activates a plane inclination arrow for adjusting the elevation nodes. You can either move the slope node manually or insert a precise value of elevation. For instance, set an elevation of 1.5 meters, corresponding roughly to an angle of 42 degrees. Alternatively, insert a generic volume in the 2D or 3D environment, defining its 3 dimensions and, if needed, additional details such as textures. Now, you are ready for the insertion of the inclined surface object. Again, access the dedicated editor, trace the perimeter, and switch from horizontal to sloped for adjusting the elevation nodes. This time, to close the gap graded on the side of the inclined surface, enclose the perimeter with an enclosure object and adjust vertex heights as needed. Add materials by selecting them from the library. In this case, roofing material and a brick-type material for walls have already been used. Continue building the BIM model with various objects. For example, consider nearby shadows caused by a chimney, which can be inserted directly over the roof in the 3D environment. Now let's move on to the next step and create the area dedicated to our photovoltaic system. To define the PV installation surface, use an object that automatically detects the available surface from the modeled site. Assuming the PV design procedure is complete, this result will enable us to identify the shadowing effect of the chimney even at different moments of the day. We'll delve deeper into this during a numerical analysis of the loss of production due to shadows over the modules later on. Now, let's explore the Assisted Design tool, a step-by-step guided procedure. This time, import a complete 3D IFC project as a base model for designing our PV system. As seen before, start by inserting the photovoltaic field, the surface dedicated to module positioning, and then access the Assisted Editor. This smart design tool provides a comprehensive summary of the best PV performance layout, with efficiency ratings at different tilt and azimuth angles, based on the monthly irradiation values for the selected site. Next, the software suggests a range of preloaded PV modules. Set the module arrangement method. Choose your preferred design criteria, such as maximum, considering spacing between modules and their distance from the surrounding surface edge. In the Balance of System dialog, redefine losses for each system type. The table allows data filtering to find the preferred PV module type or manufacturer, or even filtering using a desired property. In this case, select 250 watt panels. Once these selections are made, the assisted design procedure calculates how many modules can fit on the available surface and shows the calculated physical parameters based on the specified power design criteria. This makes Solarius PV an indispensable tool for precise PV system design. This demonstrates a quick modeling process using a few of the program's available objects, but other methods are also available. Now, for the sake of this example, we will insert other photovoltaic surfaces to check the production results in different conditions. Let's try a vertical surface located on a parapet. Select the field and access the editor. Define the properties of our system, such as the tilt, in this case, 90 degrees, and the desired module model. This is the visual result of the system. Assuming we want to implement a new small structure to accommodate a third system, we can use one of the many 3D blocks available in the library. Take a step further now by adding other components like the PV generator object and the general switch panel. These versatile methods allow for efficient and precise PV system design, making Solarius PV a valuable tool for professionals in the construction industry. The generator design follows the same dynamic as the photovoltaic system assisted tool. It is a dedicated editor that guides you to quickly choose among compatible generators, excluding those that cannot be connected to the chosen module's model, helping you avoid painful and costly mistakes. It provides all the technical information provided by the manufacturer. And in case you need to adapt the result to a custom situation, you can always go back in the procedure and change your design decisions, as well as those customizable parameters. Another powerful feature in Solarius PV is the Switchboards Assisted Design tool, which handles electrical connections and single-line diagrams, a critical aspect of PV system design. Let's explore this feature. Start by selecting your preferred language for reports and outputs, meter type settings, and other parameters. Next, move on to cable type selections and positioning methods, vital for calculating heat dissipation. Define the installation method and the room temperature as well. Specify the types of circuit protection devices you want to use. You'll notice a vast selection of device types and models. In this example, a specific circuit breaker is chosen. With this information available, the software will automatically generate branches of the electrical single-line diagram. You can edit and customize cable settings, protection devices, and the single-line diagram sections to meet specific requirements. The software also allows dynamic updates. For example, if you change the cable length, the voltage drop calculation result is updated in real time, and the tool will also alert you in case of incoherent values. Use the calculator tool to check and determine the minimum cable section required to keep the voltage drop within the maximum limit. Having to deal with multiple separated systems, it comes in handy to have a function that highlights the connections between the systems and their generators. Now, before leaving the 3D modeling environment, we will certainly want to export our model in a new version that includes all the objects we inserted and the technical information that they bring. To do so, we just need to export the project in the most open and commonly accepted format in this industry, the IFC. Alongside OBJ, SketchUp or CalAda, ensuring your project is ready for seamless collaboration and integration. Solarius PV also allows you to generate an entire set of project drawings fully customizable and dynamically connected. This basically means that whatever changes are made in any part of the PV BIM model will also dynamically update any connected drawings instantaneously. You can easily generate all the necessary construction drawings, comprehensive of any measurements, tags, and labels, by using the Area View Generator tool. Simply select it from the menu and apply it to the workspace area. Customize it using the various options in the Properties box and fine-tune with shading effects and shadows in the Graphics tab. This method also applies to cross-sections and elevation views. You can trace a line, and new views are added as subnodes. You can add as many elevation views as necessary. To add construction details, use special objects that zoom the view to a specific part of the project, providing additional information as required. Now, let's move on to composing the project working drawings. Simply set up the desired page format and drag and drop the previously created drawing sets to the working drawing sheet and arrange them as preferred. It's so simple and direct. We can add external references, such as tables, data sheets, and of course, when we need to print or export our documents, we can choose from multiple file formats: Word, export as HTML, create a PDF, or export as a DWF. Let's now go back to the area view. If we arrange the two windows side by side, notice that here we have a support structure upon which we have inserted our PV system. Also notice that whenever we change a property in one view, the same changes are instantaneously applied in the other window. In this particular example, we are enabling the shadow simulator. Let's now have a look at the generator node in the Project Navigator structure. From here, we can access a specific section for each PV field. These were modeled in the 3D environment to which we also have the relating technical information. By opening the Irradiance tab, we can check and work on the radiation data in relation to the time factor. For example, here we can see the monthly average irradiance compared to the hourly irradiance VOVs that can be measured on the module's surface. As you can see in the 3D environment, this photovoltaic field has been installed in such a position that the shadow of the building is affecting the modules during certain hours of the day, and of course this effect is more or less important during different periods of the year. So, how can we take advantage of the great flexibility of Solarius PV to have more accurate data for our project? Going back to the irradiance table, we will decrease the radiance factor of a certain percentage, taking into account the shadowing effects during the day for each month of the year. The chart results give us already an idea, from a graphical point of view, of the amount of radiation that the system will be receiving during the year. But we can also have a precise comparison between different design proposals that we're previously working on. This is a useful tool because we can easily identify, for example, which solution turns out to be more convenient in terms of system productivity and cost. The financial analysis tools are fundamental when it comes to deciding the best design solution in terms of investment and financial planning for our clients. In many cases, a good PV system design can also pinpoint technical issues that underline that investing in PV generators isn't such a good idea in terms of payback times or other valuable indicators. Being able to provide expert professional advice also means avoiding investing in a system that won't work from a cash flow point of view. So let's take a look at how Solarius PV can help understand project feasibility from a cost estimate point of view, leading down to a full financial assessment. In this section, we have a full summary of our system from an energy production site. But we can also add the system cost data by using these other cost management fields, including professional fees for design based on different evaluation methods, one-off costs, maintenance costs, periodic costs, and so on. But we also have an integrated bill of quantities tool called Primus, which automatically extracts quantities and object data directly from the 3D PV BIM model. This is our bill of quantities with some items, quantities and costs already inserted. If we decide to have a more detailed approach, we can use this tool to produce a cost estimate with the exact manufacturer unit rates and quantities extracted from the model. Here you can see the list of components and devices coming from the previous PV system design. All we need to do is insert the unit rates in the price list editor. Going back to the General tab, we can add some one-off cost and express their impact as a percentage of the total cost. We can also add periodic cost here following the same procedure. In the Cost Summary tab, all the costs data are updated, not only numbers but also charts, the most comprehensive set of financial analysis charts that we can choose from. In the Consumption Profiles node, we can define the typical energy usages for creating a time period-based energy consumption analysis. So, we can insert our devices or appliances and set their power ratings, as you can see here in the device list. We can add all of the devices we have in our household to have a precise idea of the energy usages. From here, we just need to drag and drop the desired profile over the consumption node. Now we have all the device and their consumption applied to our project. As usual, we can modify this data by entering the editing window. From here, we can decide month by month the consumption behavior. We can even decide, in an extremely accurate manner, the consumption at every minute of the day. We can actually make a precise plan of the annual consumption of any single device connected to our system. Following through with a brief explanation of the financial analysis section, you can see the useful consumption data table organized according to our installed devices. A useful summary also provides an organic view of our monthly consumption levels, expressed in kilowatt-hour. Here we can check the hourly energy consumption relating to each device present in our household or industry, both numerically and graphically, taking advantage of charts, filters, and different data arrangements. This data is organized and viewed according to the 4 tabs below. The Consumption Coverage tab provides valuable insights as to the energy demands for our appliances at a daily or monthly basis, expressed also via these easy-to-read charts which can be customized by the user. In the Profitability node, apart from the typical parameters that help us determine the different KPIs, we have some useful data input fields including rate types, export and feed-in tariff, and direct access to the main financial indicators under the Charts tab, such as net present value, internal rate of return, cash flow and expenses and income sections with the relevant charts that we can also save and export. Switching to the Customize tab, you'll be able to activate or deactivate certain tables and charts for an improved data consultation experience. The Documents node contains our two main project reports: the technical and financial reports, which are generated automatically, and for which we have full control over the chapters we'd like to include, index structure, print styles, report front pages, which can be fully customized, or even decide in which language we'd like to generate your final report. Once we have made the appropriate choices, we can then move on to generating our project reports. Reports can be easily modified and exported via the internal word processor tools. As you can see, these detailed documents contain all the data deriving both from the project and site data, our solar diagram, final results for our electrical checks, manufacturer details, etc., and the same applies for the financial report too, with the same customization features. Not only that, but a comprehensive energy storage system configurator, to where we can define the type of system to install and take advantage of a streamlined accumulation sizing wizard too. Single line diagrams are automatically generated and also provide important information concerning the different components or devices and how they are connected to each other. Set up the relevant diagram printing options, add your own details, and make changes according to your specific needs, adding extra 2D detailing if required. In conclusion, Solarius PV stands as a powerful and comprehensive solution for designing and assessing photovoltaic systems. Its user-friendly interface, step-by-step design process, and integration of various tools make it an invaluable asset for professionals in the construction industry, including architects, engineers, and BIM specialists. With Solarius PV, you can streamline the entire design process, from site assessments and shading analysis to financial feasibility assessments. The software's ability to generate construction documents, financial reports, and technical analyses automatically saves time and ensures precision in your projects. Whether you're designing PV systems for residential or commercial use, Solarius PV empowers you with the tools to make informed decisions, maximize energy production, and optimize your designs. This software is a valuable companion for professionals in the field, providing the means to create sustainable and cost-effective solar PV systems.